Welcome everyone to again a webinar that is organized in light of the sound control cost action. And today we have Aurélien Madouasse as a speaker, and he's going to present us something about the STOC 3 model, a Bayesian hidden Markov model for output-based surveillance. Aurélien graduated as a veterinarian from Nantes in 2006, and he subsequently performed a PhD on mastitis epidemiology in Nottingham in the UK, from which he graduated in 2010. Since 2012, he works as an assistant professor on epidemiology and cattle health diseases in Nantes. And today he's going to present the final results of the model to estimate freedom from infection, which he developed as part of an international project called STOC 3. So before we start, some technical issues or some technical notes. Let's see if my presentation, okay, yes. Well, please, I already noticed everyone has the camera off and the microphone on mute. If you have a comment or question, please raise your hand or enter a comment in the chat and we will keep track of the questions. It's up to Aurélien if you like the questions in between, Aurélien of at the end. So please notify us about that when you start your presentation. And of course, when you want to ask a question in person, unmute your microphone and turn on your camera. The last notification is that this webinar will be recorded and published on our sound control website for interested people. It's only the webinar that will be recorded. So if we have some discussion afterwards, then we will stop the recording. So if you don't like the fact of being recorded, of your question being recorded, don't worry. At the end, we will stop recording and then you can still ask your question. So I will stop to share my presentation and give the floor to Aurélien. And I hope you will enjoy this very interesting webinar. So Aurélien, the floor is yours.
So thanks, Inge, for the introduction, and hi, everybody. So I'm going to share my screen. So can you see my screen with the slides? Yeah. So yeah, if you have any maybe short questions, I can answer them during the presentation, but maybe more important questions, we can keep some time at the end to discuss them. So yeah, I'm going to present you the STOC 3 model. Which was developed as part of the STOC 3 project. So I've put the link here. And so also the slides, these slides are available from a link that should be available in the chat. So you can download the PDF file of this presentation if you want to have them on your computer. Here is the plan of the presentation that I'm going to start straight away. So some introduction on the context, which is about infectious diseases of cattle. So on one side you have regulated diseases, which are regulated for various reasons, either because they are public health threats or because they have a high economic impact. And usually for these diseases, you have a strict legislation on how to perform surveillance in order to prove that you're free from disease. And usually in those cases, every country has to perform surveillance in the same way to get a comparable output. So this is what you could call input-based surveillance. So you assume that because everything that goes in is the same, you will be able to compare easily what comes out of your surveillance program. But there are also a lot of non-regulated diseases, some of which are really important, and so that their importance justifies some either control or eradication programs. So examples of such diseases in cattle would be BVD or paratuberculosis. So in those cases, there is no legal prescription on the way to perform surveillance, which means that you have an important diversity in the design of surveillance programs. And so in those programs, the free status that's given to some herds can have a different meaning depending on how surveillance was done. And this creates difficulties when trading animals between herds that participate to different programs. So this would be especially between different regions or countries. And so the objective of output-based surveillance is to produce an output that is comparable regardless of the inputs that was used in surveillance. So really the problem of STOC 3 was to design a method that could take inputs from diverse surveillance programs and that could produce an output that that is comparable. So that was really our objective, our initial objective. And the structure of the method, or the model in this case, is determined by what is common across surveillance programs. So the structure of the model must reflect what is common to all surveillance programs. And the probability of freedom from infection, because we're interested in infectious diseases, must be determined from the available surveillance data, so collected usually as a test results, and should also be able to incorporate relevant knowledge such as test characteristics. What's common between these programs? So we were interested in control programs, which means that we were interested in cases where the prevalence was not zero, so the disease was still present in a region. So the objective of the program could be diverse. So this is disease control or eradication, and but the program is usually organized at some levels such as region or country. And the control program relies on a surveillance component for the identification of infected herds or animals. And usually in those programs, you have a following detection, you have a control phase that is implemented to usually remove the infected individuals from the infected herds. And also usually, in these cases, surveillance is performed in all participating herds. So you have herd level information in all herds. And these herds are repeatedly tested over time. So you get longitudinal data in each individual herds. And maybe I should add that usually these data are correlated. So when you're infected at some point in time, it's very unlikely that you've got rid of the infection on the next time point. And another feature of these surveillance programs is that tests are usually imperfect, so which is more or less important. So usually in the case of BVD, the tests are quite good, but for diseases such as paratuberculosis, the sensitivity of testing can be quite low. And so the characteristics of these tests, so their ability to correctly identify infected herds is measured by two parameters, which are sensitivity, which is the probability of getting a positive test in a diseased herd, and specificity, which is the probability of getting a negative test in an uninfected herd. And so for each test, you have some uncertainty associated with the test result. It could be either a false positive or a false negative. And so this is represented on this small diagram where you have the true status regarding disease. So here you can be uninfected or infected. And then you have a test result, which can be either negative or positive. And so infected herds have a positive test with some probability, which is a sensitivity. And then a negative test with a probability that's 1 minus the sensitivity. And uninfected herds can have a negative test with a probability that is the specificity, and a positive test with a probability that's 1 minus the specificity. Okay, so yeah, this was the description of the problem and the main features of the problem. So the modeling framework we chose. So our objective was to therefore predict herd level probabilities of infection or freedom from infection, because once you have infection, you also have freedom from infection, from longitudinal test data collected as part of surveillance programs against endemic infectious diseases of cattle. So the retained modeling framework should allow the use of this longitudinal data. So account for the correlation in consecutive test results and account for imperfect test information. So the type of models we chose for this is called hidden Markov models. And these models, they model a latent discrete variable. So latent means that you do not observe it directly, with a Markovian dynamics, whose state at a given time determines the distribution of an observed variable. So the discrete variable, so the model outcome can be in one of k states. So in the STOC free model, we only had two states, so either infected or uninfected. And so this discrete variable was observed imperfectly, so this is what made it latent. And this latent status, so truly infected or truly uninfected, determines the probability of a negative or positive test result through a test sensitivity and test specificity. And the last part, the Markovian dynamics, means that our model works in discrete time steps. So time 1, 2, 3, and 4, so only discrete values. And the true latent state at one moment, one time step, so either infected or not infected, only depends on the state at the previous step. So yeah, and this determines some transition between all the possible states between two consecutive time points. Okay, so yeah, so that's really the essence of hidden Markov models. So discrete outcome that is measured imperfectly, and this latent discrete outcome determines the state of some measure, which in this case is a test result. So this can be represented as follows. So here you have some state at time t. So you do not observe it directly, but you get a test result. And the relationship between these two is a test sensitivity and test specificity. And your state at one point in time only depends on the state at the previous time. And so the first time step is a bit peculiar because you do not have anything before it to determine its value. So you have to initiate your first time step. Okay. And so this can be described with statistical distributions. So this is same as on the previous slide. So you have your true state at some point in time. So this state is a Bernoulli variable. So it's like flipping a coin. So you are either negative or positive with some probability. And so this is the probability of being status positive, so meaning probability of being infected. And so if you were not infected at the previous time step, you have some probability of new infection that in the model we called tau 1. And if you were already infected at the previous time step, you have some probability of remaining infected, and we measure this with a tau 2. So this is what is described here. So at any time step, your probability of infection is only determined by the state at the previous time step through some probability of either new infection or of remaining infected. Okay, and so in the STOC free model, we added some one complexity to this. We said that your probability of getting infected could be influenced by some risk factor. So I'll show an example later, but so here we used, for example, the number of cows introduced in your herd as a way to increase your probability of new infection. So yeah, your probability of new infection could be influenced by some risk factor. And so in the model, we incorporated this using logistic regression. Okay, so here are some examples. So this is just a summary of what I just said. So you have some initial probability of being in a state. So you have pi1, which is the probability of being infected on the first time step. And then you have four possible transitions. So you can get infected with some probability tau 1. remain infected with some probability tau2, remain uninfected with a probability 1 minus tau1, and eliminate infection with some probability 1 minus tau2. So this is in fact quite simple as a model. So you have a very few parameters describing your entire system, which is kind of like of an SI model. So that was for the dynamics, and then for the link between true status and test results. So this is what I just said earlier. So your probability of testing positive is 1 minus the specificity if you are not infected at some time, and it's the sensitivity if you're infected at some time. So your true status determines your test result. And so again, you have 4 possible combinations. So positive test result in an infected herd through sensitivity, a negative test result in an infected herd through 1 minus sensitivity, negative test result in an uninfected herd through specificity, and a positive test result in an uninfected herd through 1 minus specificity. Okay, so that was for the model structure. And so our interest here was really to predict the probability that a herd was infected at the time where we run the model. So at the last point in time for which we had data. So we wanted to predict probability of infection now, given all the historical data. So these historical data were used to learn the parameters, and then they were used to predict. So to predict the probability of infection on the last at the last point in time. So this is really the thing that we are most interested in with this framework. So this is a summary of the different parameters, but I'm going to skip this because I've already explained that. And this is really the equations that summarize the model, which you can see. Yeah, it's pretty simple. So you have some first initial state, probability of being infected at the first point in time, which is described by a probability of infection. And then for each later point in time, the probability of infection is described with 2 parameters, so tau1 and tau2. And then this true state determines some test result through sensitivity and specificity. Okay, and when you add a risk factor, the only difference is that your tau1 variable is evaluated at each point in time through logistic regression as a function of some risk factors, matrix of risk factors. Okay, so that's for the model structure. Now for the implementation. So we implemented the model, so meaning that we performed the parameter estimation and prediction in a Bayesian framework. So we thought this was useful because this kind of framework allows you to incorporate available knowledge, so notably on test characteristics, using prior distributions. And in developing the model, we compared 2 different implementations, either using the JAGS program or the STAN program. So both models were equivalent but coded in a different language. And then we put everything in an R package so that people could use the model we developed freely. So so R is, I guess most of you are familiar with R, but it's a programming environment for data manipulation and analysis. So it's widely used and it's free. And a package is a set of functions that are gathered in the same directory to perform some specific tasks. And so you can install the package and use it on your own computer. And the stock free package is hosted on a platform called GitHub. And I'll show you later how to get this package and install it on your computer. And what it does, so there are various functions in the package to format the data for analysis. to select the risk factors to include in your model, to set model priors. And then once you've done that, you can call either JAGS or STAN to perform the estimation and get the results back in R to summarize the model results. So yeah, so the package is hosted on GitHub. So you can go to this page and you'll see so what's called a README file on which you will find all the instructions to install and run the code on your computer. Okay. Yes, so this is what the GitHub page looks like. But what's important, yeah, if you go to this page, scroll down, and you'll arrive at this README file that you can where you can see the different instructions to install and use the package. Okay.
There is a question in the chat. Shall I ask him now, or do you want me to hold it on until the end? Because I think the people are not able to unmute their mic and ask him the question yourself.
Yeah, I can answer this one because I'm going pretty fast. So
okay, shall I read it out loud?
Yeah.
So first of all, very interesting presentation. Does your model assume that the sensitivity and specificity of an animal level test is constant in time and across population? For some infections, the sensitivity of an animal level test depends on age at infection or the infectious dose, and thus on the prevalence of infection. Is your model able to deal with such a complex situation?
No, so currently the model works at the herd level. So meaning that you need to have, for each point in time, you can have only one aggregated herd level test result. So we are not able to incorporate animal level test results. So we've tried this initially, but so by modeling a number of positive out of a number of tested as a binomial distribution, but there were several issues with that, notably that with BVD, it was not easy to see what was the denominator, because you've repeated your test over time, and then the animals that were negative at the previous round of testing are unlikely to have become positive. But then what's the denominator of your binomial? And then the other difficulty was that you'll usually test a group of animals within your herd. So you could test some number of animals between 1 and 2 years, for example. And it was not easy to see what was the sensitivity of the resulting test result, because it combines the true test characteristics to your sampling, because the probability of infection is not homogeneous across age groups in your herd. So we've abandoned this animal level data, which we may come back to it later, but it was complicated, we felt. So that was the first part of the question regarding herd level or animal level. Then for complex situations such as sensitivity or specificity changing over time. So this is possible with the current model. It just involves, because the model can use several tests. So if you have 2 tests, you just need to enter the test ID and specify different sensitivities and specificities for the different tests. So what's currently possible is to create a different test for each possible situation and enter the relevant sensitivities and specificities associated with each context. So yeah, I hope this clarifies, but you can unmute yourself and tell me if I didn't answer correctly. Okay, thank you. So yeah, I'm going to move now to the application to the surveillance of BVD on a French data set. Yeah, so we applied the model on a quite simple data set. So it's not an ideal data set, but we've submitted a description of the model with this application. So which is why I'm going to present it a bit longer, in a bit more detail. So yeah, these are surveillance data collected as part of dairy cattle BVD control program in so Loire Atlantique in France, which is the region where I am based. And in this program, all the herds are tested every 6 months. And the test consists in performing an antibody ELISA on bulk tank milk. So here it's good because we have one herd level test result. And we had data from 1,687 herds between 2014 and 2017, sorry. And so the data look like this. So this is the number of herds tested. And usually they are tested by every 6 months, so that you have campaigns of testing where each herd is tested over a small period. And then nothing happens and they're retested later on. So we had 3 years of data. And so we were interested in the probability of infection or the probability of being positive, status positive, for each herd on the last month of surveillance. So here I think it was October 2016, the month that was predicted for all the herds. Okay, and so we compared 4 different model settings, incorporating different hypotheses, and we tested all 4 models in both STAN and JAGS as a way to see whether the results were different. And to us, it was more so because initially the model was developed in JAGS, but we had some convergence problems, and we implemented the model in STAN later on, and this was a way for us to check that they were giving consistent results and to see which one was working better. So yeah, we had 4 different models, which I'm going to show in more details later on. So in the first model, we assumed that our bulk tank milk antibody ELISA was perfect. So a sensitivity of 1 and specificity of 1. We assumed that there was no risk factor, so we did not include any risk factor in the model. In the second model, we assumed that the test was imperfect, so the sensitivity and specificity were smaller than 1. And again, we did not include any risk factor. And so the third model, we had a perfect test, but we had 1 risk factor. And the last model, we had imperfect test and 1 risk factor. So this is the 4 models we compared in both JAGS and STAN. So the risk factors, initially we considered 2 risk factors after initial screening. So both the number of cattle introduced in the herd and the local seroprevalence. So that was the proportion of test positive herds in the same municipality. And after running the model, the Bayesian model, we dropped the local seroprevalence, which was not significant. So this is why we just had 1 risk factor, but this is not a limitation of the function in the package. You could add an arbitrary number of risk factors. So here it's to give you an idea of the priors we put on test sensitivity and test specificity when assuming a perfect test. And so to help, so there are various ways to construct these priors. To help in this, we, as part of the project, we wrote a small Shiny app that allows you to, if you have an idea of your sensitivity and specificity, this app will give you the parameters of beta distribution that summarizes your current knowledge about the distribution. So here, for example, I could say my test has a sensitivity of 0.9, and yeah, I'm sure it's less than 1. It's very above 0.8. So this would give you a beta distribution with parameter 30 and 3.3. And so I can test. I can also see what it gives if I make it a bit more. If I run the numbers. So yeah. So the Bayesian framework really allows you to go from what you think or what you know about some parameter and really include it in the model. So this is part of the reason why we used this kind of modeling framework. So yeah, so that was the sensitivity and specificity for the models where we assumed that the test was perfect. Then we relaxed this, and we said we not as sure about the sensitivity and specificity, so we make it a bit wider, and we expect that by putting that in the model with the data, the model will find a solution. So we will identify a sensitivity and specificity that are more realistic. Okay, so. And for the risk factors, so it works as modeling the probability of new infection as a logistic regression. So in this logistic regression, we had one parameter, so θ1, which measures the probability of new infection when your risk factor is absent. And for BVD, we assume that the probability of new infection when you have no risk factor was pretty low, so yeah, certainly below 0.2, and I can't remember what are the mode or median of the distribution, but we assume it is pretty low. And for this θ2 is how strong is the association between the risk factor and the probability of new infection. So here that was in reality that was the log of the number of cattle introduced, and we assumed that there was no association, and we wanted to the model to identify the strength of association from historical data. So it was an informative prior in this case, or weakly informative. So it was not bringing too much information. Okay, so that was for the model setting. So yeah, these are examples of prior distributions. There were other prior distributions which are described in the paper, for which you'll have the link at the bottom of the presentation. Okay, and so yeah, these are like model results. So when you have Bayesian models, the thing is the way it works, you run several instances of your algorithm. So it's iterative. So you here are 500 iterations, and so you run the several instances of the algorithm to check that they all settle to the same solution, basically. And so here you have what you could call good mixing, because I have 4 chains and all of them seem to explore the same parameter space. So they all end up in the same place, roughly. Okay, so yeah, this one looks good. So that's the model 1, where we assumed a perfect test characteristic. So we assume that the test perfectly measures the state of infection. And so in this case, both the Stan and JAGS model seem to work well. So it's all looking good. In the second case, we assume that the test was not as good. So this is this sensitivity and specificity. And here the Stan model does well, but the JAGS model really they are not mixing well. So this is what you could call autocorrelation, because the value at each iteration depends very much on the value at the previous iteration, which means that you do not have independent samples from your posterior distribution. Even more than that, you're not sure that the algorithm has settled in the right place. So you do not know whether you can trust these values. So the bottom line on this slide is that the STAN model seems to work much better, and especially when you say that you're not too sure about your prior information on test characteristics. Now, if you look at the parameter estimates, so this is the model results is so we've given prior information to the model. So here, so that's model 2 and 3, where we said that we do not know, we are not sure about test sensitivity and test specificity. So this measures what we used as input in the prior distribution in the form of a box plot. And this is the posterior distributions for STAN and for JAGs. So this is where STAN thinks the true value of the parameter is after having observed the data and taken the prior distribution into account. So, so what you can see is that, when you assume perfect test, everything ends up in the right place. So you assume that your true state is your test result. And when you say it's your test is imperfect, so usually the model assumes higher sensitivity and specificity. And the estimates between STAN and JAGs are kind of consistent. So there is an overlap in the posterior distributions. Although this does not look reassuring. Okay, so that's it. So these are the results for the test characteristics. These are the posterior distributions for the infection dynamics. So that's so here are the estimates of the parameters after observing the data and having taken the prior information into account. So for the probability of new infection, so here you can see that the model estimates that the probability of new infection when there is no risk factor is around 0.3. And when you have a risk factor, this probability of new infection, this is the probability of new infection when the risk factor is absent. Okay. And so this is the probability of remaining infected between consecutive time points. And you see that the model puts the posterior distribution much higher than the prior distributions. Okay, and this was the risk factor. So here, so it was only included in model 3 and 4. So perfect test, imperfect test. And if you plot the predicting effect of introducing an increasing number of animals, you see that you have a quite significant impact of introducing cattle in your herds. This impact does not is not very different between the two models, and you see that you can for 100 cattle introduced, you reach a probability of new infection of 0.3, which means that it will increase the sensitivity of detection, or at least label more herds as potentially infected. Okay, so a few words on these parameter estimates. So they are consistent between JAGs and STAN, roughly. So the posterior distributions are much narrower and sometimes far from the prior distributions, meaning that the data contributes to your estimation, to the posterior distributions. And so the number of cattle introduced increases the probability of infection, so probably increases the sensitivity of detection. So now the real interest in this model is the predicted probabilities of infection for all herds. And here these probabilities of infection were predicted on the last month in which a test result was available, which was October 2016. So here is a plot of the posterior distributions for these predicted probability of infections for all herds. And you see that they're roughly the same, and basically it's bimodal. So here are the herds that were considered not infected on the previous month. And for these herds, they have a certain probability of new infection. So basically, this is the tau1 parameter. And here, you have the probability of basically remaining infected. So these herds were considered infected on the previous or on the month before prediction. Okay, and so in red you have the STAN predictions, and in green you have the JAGS ones, and yeah, they're roughly the same. Or they're consistent. Now I've pulled out 4 different herds to show you what it looks like. So this first herd, so we had 3 years of data with 2 test results each year. So it's basically 6 test results. So this herd had a sequence of 6 negative test results. And it had no test result on the month before the month of prediction, which is the reason for this hyphen. And it introduced no animals. So basically, this is the most favorable condition, and you see that it has a very low probability of being infected. So this herd had the same sequence of test results, but it bought around 200 cattle in the month before prediction. And you can see that in the model with no risk factor, the probability of a new infection was pretty low. But when you took the risk factor into account, the predicted probability of infection was much higher. So meaning that knowing the risk factor changed your predicted status about this herd. So this herd had a sequence of 5 negative test results and 1 positive test result in the end, but introduced no animal. So you can see that assuming perfect test results, you had a very high probability of being infected. But when you assume that the test is not perfect, you have varying, differing probabilities of being infected. Meaning that given the long sequence of negative test results, the model wasn't sure about this positive test result could as well have been false positive. And the last one is a herd with a long sequence of positive test results, and then a very high probability of being infected. Okay, so I'm almost there. So the key messages. So the model we developed, it predicts so herd level probabilities of infection from longitudinal surveillance data. So the estimation and predictions are performed in a Bayesian framework, which is convenient if you want to incorporate available knowledge on test characteristics and disease epidemiology. From the comparison of the 2 implementations, so STAN and JAGS, we found that the STAN was much more reliable and able to account for imperfect test information, which was kind of expected. And further work that could be considered is how to categorize herds into infected or not infected from the predicted posterior distributions. Because, so as you can see here, you get like a kind of histogram, but you need to translate it into a decision into free from infection or not free from infection. So this still requires some thinking. And one difficulty we had, and really that was a major issue, was to the definition of prior distributions, because there is no easy way to define a herd level prior distribution from known test characteristics and combining the sampling scheme, so which accounts for the fact that different groups of animals in a herd do not have the same probability of being infected. So this was a major difficulty. I've duplicated that. So so all all the code and documentation are available from GitHub. So if you want to test the model on your own data or using the data in the package, you can install it from here. We've submitted a paper to something called peer community in, so it's currently under review, but the preprint is available. So if you want to know more about the model structure and the application on BVD I presented, and this presentation and some more materials, such as a tutorial, are available also from GitHub, so you can visit this page. And feel free to use and improve the model. Okay, so thank you for your attention, and this is everything I wanted to say to you today.